Thanks for the organizers to invite me here. And I have been really thinking hard what I should talk about. And in the last couple of days, thanks to all the speakers, I've learned so much. And only one or two speakers mentioned about quantum work. So I thought maybe this is going to be of interest and relevant to everyone is doing. So that's me, Jingbo Wang. I came all the way from Perth, Australia, and I currently lead a fairly active group of researchers in quantum information, quantum simulation, and quantum algorithms. So we actually published a book almost 10 years ago now. Time just goes by so quickly, but as they indicated here by the title, I have a strong physics background. Just wonder how many of you is a physicist? Oh, great. Okay, all right. So that book is focused on how to implement quantum work via many different physical systems, including linear optics, NMR, cavity QED, or quantum optics, ion traps, and basically whatever you can think about manipulating particles at the fundamental level, and that can be used. Whether it's efficient or not, that requires study. So that's what this book was all about. However, we did cover, at that time, explored applications and also describe the foundations. So today, I'll start with an introduction to quantum works, and then I will possibly don't have time to talk about application. I want to say to the same, this is very important. Quantum work has been proven to be universal computing. Whatever a quantum computer can do, and we can do it in the world of quantum workers. And I will be maybe focusing on how to use a quantum circuit to implement the kind of quantum works I'm going to introduce and talk about, because there you can actually count the number of gates and get a very clear picture of its complexity. I think that's important. So that's going to be my talk. All right, very brief introduction about what is quantum working. We are all familiar with classical working. We go to visit a city, we don't know where to go, we just randomly walk around. But if we have sufficient time, we would know the city pretty much well. So classically, let's talk about the simplest work along a line. So you start at any position, and then you throw, that's 100% at position 0. And then you throw the dice, depending on whether it's face up or down, you move left or right. Okay? And then you repeat that process, and gradually you will depart from where you started with, and in general it's a Gaussian distribution. Okay? In the quantum world, nothing much is really different. The only exception is this quantum worker can work both ways at the same time. So he has this quantum dice, which can have certain probability moving left, certain probability moving right. I should say amplitude, yeah. And so that's the familiar operator, coin operator, and then you do the translation. So this, you repeat, and then you will have this interference pattern coming along instead of just a Gaussian. And it's much more interesting, and it moves away from the center much faster. Just as a comparison, at the same time, and the classical worker has hardly left where they started with, but the quantum worker actually emerged far away. Yeah, it's a quadratic speed up. So my student actually created this artistic impression of me as the classical worker walking along and randomly, and of course you can see it's going to gradually depart from where I started with. And if I'm a quantum worker, and then I will be work at the same time simultaneously traversing different paths. all at the same time with some kind of amplitude. And the amplitude carries phase, therefore, it will have interference. So even though this person, or me, quantum worker, can come here and here, yeah, seems to have twice the opportunity to come to the center, but it's a destructive interference, and you carry on. So this is how you get a very interesting pattern emerging after a certain number of times. And things can get even more interesting if you introduce more than one quantum workers, because the workers can interact and they can get entangled as well. So this is two workers hold hand in hand, working in a very similar fashion. All right, each of them carry a coin, a collective coin, and they start somewhere together or apart, and then you apply the same logic, and the system will evolve. The quantum workers can have different quantum properties, and if you put it like this, entangled, but with a minus sign, and you kind of mimic the behavior of a fermionic particles. And then you do the simulation, this will be what you get. And as you can see, these two workers try to get far away from each other as possible. You switch the sign and become bosonic. Yes?
Just good. The entanglement is just because of the initial state, not because of the coins. The coins are separable, right?
Yeah, here, but you can, yes. Yes, so you really have a lot of ways to change the dynamics in a very much controlled way. Very, very good question. Yes, they can entangle in position, they can entangle between the two particles, and you can create entanglement along the way.
Can I ask a follow-up?
Yes.
So does the entanglement decrease as they move apart, stay the same?
It's changing.
Okay.
Actually, we do have a paper. If you search my name and entanglement dynamics, and they change. Yeah, and also depend on what you measure. Entanglement is a quite complex, but very, very, very good questions. Everything, yeah. So you can see they can be together with very high probability, almost like the Hall-Mandel kind of effect. They want to bunch together. So someone has already suggested that there's a lot of things we can change, we can manipulate, and we can introduce ion, right? We don't have to just use minus or plus. We can introduce arbitrary phase, and people call that anion, right? And then you can say, okay, those particles maybe they experience some kind of molecular interaction, and then you can actually engineer almost anything you really want. So that provides a really powerful platform for you to engage, to design, and to manipulate to get what you really want. Okay. So of course, things becomes much more interesting if we allow them to work around in a much more complex structure, not just along a line. So any structure can be mapped to a graph. So a graph is some points connected by adjacency matrix in some way. And then classically, this is what you have. You have a probability at any time, any point in time, and then you have this translation matrix, transition matrix, and you map the probability from T0 to T1 and apply it, T2, T3, and then you know exactly what you are going to get after T number of steps. So quantum mechanically, you keep the same mathematical structure. And instead of playing with probability, you play with amplitude. That's what we call wave function. And if we consider closed system quantum work, and the transition matrix needs to be a unitary. Okay. Yeah, let me just give you an example. And this is a very arbitrary graph, and that's self-loop. And let's just say just one worker. And this worker lives in this helped space. And this helped space will need to have the number of states corresponding to the number of edges and at each vertex. And you start with any arbitrary wave function. And there's two steps in the quantum work. First, you mix the states. So that's the mixer. And the mixer happens at each node. So it's quite local. Okay? And then you do the translation. So you repeat that process, and that's what we call a quantum work. Yeah. So there's more you can do. You don't have to step one step at a time in a discrete fashion. You can think about like a water flow out of many, many pipes connected in a certain way, and it continuously flows. Classically, it's the stochastic Markov chain. And a very simple differential equation. And you map the probability by an operator continuously in time to a probability at any later time. And the probability, of course, is a vector, right? You present the probability at each node. So quantum mechanically, you preserve the same mathematics structure, and you play with wave function, which is a complex amplitude. And so the H becomes an operator, and you put an I there. And this is what everyone seems to be talking about, Hamiltonian simulation. And solution of the Schrödinger's equation, if the Hamiltonian is time independent. So this is actually what we would call continuous time quantum work. It's continuously working in a quantum fashion. And the one I just described, step by step, you mix and then you work. Really, it's a permutation. And that's what we call discrete time quantum work. And if the graph has no direction, and the adjacency matrix would be 1 if they are connected. So if A connects to B, B connects to A. So it's symmetric. Because it's symmetric, the adjacency matrix, or the graph Laplacian, is Hermitian. Therefore, exponential of the IHT is unitary. So it's a closed quantum system. And if you design the mixer, which can be anything really, but if you want to preserve the unitarity, and then it's a unitary evolution, it's what we call a closed system quantum evolution. But we can do more. We can introduce directed graph and with weighting. So the only thing which happens here is it will break the symmetry. So here, in general, the B, the graph adjacency matrix, will no longer be symmetric or Hermitian, and therefore, this is going to be non-unitary. And similarly, that translation is going to be biased, and therefore, it's not going to be unitary. But it's okay. We call it non-unitary quantum work. We want to keep that quantum work as the basic vocabulary. And then under this umbrella, there are many, many studies, and people characterize them as chiral quantum work. Chiral quantum work is nothing really too different. Instead of having an adjacency matrix of only 0 and 1, you have a phase. You have a unit vector, and as long as you make sure it's the ij term is conjugate, complex conjugate of ji, it's Hermitian, and then everything I talked about so far works. So, but it adds bias because one direction is theta, the other direction is minus theta. And there is a really interesting group of people studying, led by Zigdy, of course. This is called Zigdy quantum work. They introduce a dual space. And that in the dual space, you can build in the direction, the directional information of the graph. And then we actually did a lot of work on this PT symmetric quantum work. And it's a special kind of Hamiltonian. It's not Hermitian, it's a pseudo-Hermitian, which has a really nice property of all eigenvalues are real. And because it's not Hermitian, it's not unitary, it doesn't conserve the norm. However, the amplitude bounds. So people can still do experiments and study it and implement directed graph quantum work. And of course, you can introduce stochastic variables. And when the work is working, there is uncertainty there. And it can use to simulate the stochastic equations. And in particular, we have been using that to look at mathematical finance, like portfolio optimization, option price, where this stochastic variables and is inherent in the system. So that can also be talked about under this huge, this big umbrella or the very, very powerful platform of quantum works. Okay, I hope that motivates the study in this way. And if you do I just did a very quick Google search. I said, Google, tell me what are the applications of classical random walk. It gives you a huge list, much longer than this. And naturally, we ask, can we apply the quantum work? It's analogous version to help us to do something useful. So this is one of the milestone paper by Andrew Childs and others. So they looked at this glue tree back-to-back structure, and I'll show you what happens. So here you can implement a classical work. You just at each intersect, you say the 1/3 goes back, 1/3 goes left, and 1/3 goes right. And because this random connection in the middle, it's very difficult to get past that barrier. However, if you do it quantum mechanically, the same structure, and you can see the interference is constructive at the exit point. So it looks like you hit no barrier, and you emerge exponentially quicker at the other end. Yeah. But I want to say this is like treating the one quantum work as a black box, assuming it can be done, right? And then, you just need the number. What I'm showing you is really the number of quantum works required. But no one knows how to implement quantum works on that arbitrary connected graph. Yeah. So over the many years, we have looked at applications of quantum works. And we have been talking with lots of people, collaborating with lots of people. And currently, one of our focus is to talk with end users, really want to understand what's the bottleneck of their computational tasks, why where's the difficulty, and try to see if we can do something useful there. So particularly, this will rely on, we can efficiently implement the quantum works, which are the building blocks, right? If you say, okay, number of building blocks is polynomial n, but if the box itself cannot be done efficiently, I think that's many of you are doing that kind of work, how to implement that Hamiltonian simulation. And here we do more, right? And then you can't really talk about the advantage of whatever algorithm you design. So today, I think I will focus, but if anyone wants to know anything about all the things we explored and some proved, some numerically demonstrated, please come to talk with me. Or you can go to our website, and that has a list of our recent publications. As you can see, we did financial portfolio, and we did vehicle routing, we did logistics, and we looked at network complexity, and we searched for ways to do pattern recognition, and that requires graph similarity, and we spend a lot of time on graph isomorphism problems, and so on and so forth. Yeah. So, but in the remaining time, I will focus on how to open that black box, actually make sure that building block can be done efficiently. When I say efficiently, I'm really aiming to do it exponentially, right? Yeah, not polynomially. So just a summary of what we want to do. This is the graph. Yeah, any graph. And you can run it in discrete time. That's what we call discrete time quantum work. That requires a mixer and or coin and translation, which is essentially permutation. And in the continuous domain, continuous quantum work, it's Hamiltonian simulation. And then the rest, we can bundle it as non-unitary. So I'll try to do it one by one. Yes?
Can you explain what is the meaning of quantum coin? Quantum
Oh, yeah. So quantum coin, or I sometimes call it a mixer. It's just a unitary, any unitary matrix applied to the subspace of your coin space.
What is coin space?
Okay, yeah, all right, yeah, if I can go back there quickly. So here. Yeah, as you can see, this is the graph, arbitrary graph. And the discrete time quantum work has two steps. The first step is you are going to mix the amplitude around this node, or around this vertex. And how do you do that? You apply a linear transformation. That linear transformation needs to be unitary to make things simple and norm conserving. So that's the mixer. That's the coin operation. And then after that, you just do the translation. Okay, so I'll show.
So here, both C hat and T hat are both unitaries, or?
Yes, all C's are unitary. Otherwise, you get if your graph, the underlying structure is directional, and then that C is not going to be and the translation is not going to be. Yeah. Okay, yeah. So I'll talk about them each one by one. So I'll start with discrete time quantum work. Actually, it's simpler because the coin operation is actually local, right? So you apply, so the C1, C2, C3 will be the blocks in, they can be applied independently or in parallel at the same time. So these are local, much smaller space, and the local structure or local symmetry is quite important. And then the T is permutation, which is known to be done easily. While the other one, I'll leave it a little bit later, and that instantly connects any node with all the other nodes. So global structure is very, very important. So if you don't have a global, some kind of symmetry, and then it cannot be done. I want to say, in generally, this cannot be done efficiently. Everyone knows it will be 4 to the power of n in general cost. So if someone gave me arbitrary unitary matrix and say design a quantum circuit, and in general it's not going to be efficient. Therefore, we have to search for structure which will help us in the design. Yes? Yeah, I think somehow there is a 2. It's definitely 2 to the power of n. I think there is a multiplying factor there. So that's in general. So that's the number of gates you would require to implement an arbitrary unitary. Yeah. Okay, so structure, symmetry is the most important. Yeah. So let's start with some graphs which has the most symmetry. It's a complete graph. Complete graph is a graph you connect one node with every other node. And because it's so simple, even though it's dense, but it's simple. The symmetry is so obvious. And the quantum circuit is very, very simple. So this is what you do. And you use a bunch of qubits to represent the nodes, and a bunch of qubits to represent the subnodes, which is hidden, basically the edges. And you want to create, of course, a superposition, and you just swap, because overall you swap it with everything, right? So if you use that, it just a set of Harvard operation. And you don't even need to swap. Yeah, in your mind, this is A, this is B, that's fine. And then you have already implemented one step of quantum work. So let's go to reduce the symmetry somewhat and a cycle. Yeah, so the cycle is also quite interesting because you move everything goes this way, right? If the coin is positive, and you move everything goes the other way if the coin state is negative. Yeah.
Sorry, just to echo. So if by looking at this, so the number of qubits in the subnode, so that's the coin space, right? Subnode is coin space.
Yeah, yes.
And so it's linked to the number of edges that you have on your graph.
That's right. Yes, and then I deliberately put a self loop, so make sure it's 16 by 16, yeah. And so it's a cycle graph. And so you can see this coin state, because even though it's a circle, every node has only two possibilities. You use only one qubit to represent the subnode. And you apply a H and you make it to be both 0 and 1. And then this is I do have that circuit. So that circuit will increment everything to the next, to add 1, basically. And do I have that? Yeah, so it goes the other way. All right, you put them together, so it's very, very simple. And you can grow the graph to very big number, and you need log that big number of qubits plus 1, and then you can count the number of circuits is definitely just 2 times the n, I think. Yeah. So that's what we call efficient. And then you keep on going, add a little bit, break a little bit of symmetry and add some other symmetry. So this is the hypercycle, very, very similar idea. So at each point, it has 4 directions. And therefore, you need 2 qubits to represent which direction it needs to go. And then X, you go one way, other way, and Y, go one way, the other way, all together. That's one step of quantum work. And and you can design different kind of coin. And if you use a global coin here, it's okay. You just basically apply whatever coin you have and produce some kind of superposition of states, and the state determines where the work will go. Yes.
So over here, the node register contains all the amplitudes of the probabilities on each of the nodes, right? And the subnodes are representing the edges. So at the end of the circuit, like, do we have to condition on the subnodes being in the 0 state, or?
No. Yeah. So whatever you started with, so you have the wave function with all the amplitudes of all these, all these substates and states, node states and coin states, and then you evolve. And then you get to your wave function. And if you want to do it again, you repeat this, and that's how you do it. So everything evolves unitarily, to the end, hopefully, without the error. Yes, yeah. So basically, that is one step of the T and C. And then you apply T and C, over and over again. This is the discrete time quantum work. Yeah.
Is there a clear, like, this part is C, this part is T, or?
Yes. Yeah. This is obviously the C, and that's the T.
Okay, so the C is your what you do with your coins, yes?
Yes.
Oh, thank you.
Yes. Yeah. Okay. So and this is just a way trying to use not qubits. Everyone talk about qubits, but we can equally make Q trees and Q whatever, right? So if this is a complete graph, but it's not 2 to the power of n, it's 3 power of n. And if you use Q trees, and in physics, it's actually not too much more different or more difficult. And then you apply this, all these t's defined on Q trees, and therefore you can do the coin, and then you just swap. So up to now, I talked about regular graphs, which means every node has the same degree, and we want to explore other possibilities. And the first one we looked at is the star graph. I think star graph, someone may have done it before us, I can't remember, but this is a star graph with arbitrary number of branches. Again, yeah, so all you need to do is a coin operation, mix all the states, right? And then you swap it with the edges. So that's the coin, and then you swap. And you can build up this tree. This is the Cayley tree, how the Cayley tree comes from. And you can see each of this is like 3 star graphs. And if you label them properly, and it's all done by my students. So they play with and they somehow simplify and optimize, and this is what they get. And the G is the Grover coin. Yeah. So you apply, and then you swap. This is really, really, you can see this tree can expand to be very large number of nodes. However, you need log, and then a few steps. And actually, my student, Thomas Locke, extend that to arbitrary Cayley tree, arbitrary branches, arbitrary layers, and towards the end, it's that. Okay. So you can count, absolutely, very, very low polynomial, not even polynomial, I think it's linear of n, which is great, yeah. And then he pushed it further, the same student, and this looks really strange and twisted torus lattice. And I was told this has applications in string theory or something. So we look at this. Each node is actually as complicated as the one I show on the right. And the graph, the quantum circuit is not that more complicated. Yes?
How come you, in some of the graphs, use swaps to kind of spread the graph, and then in some of them you have these adder increment circuits?
Yeah.
It seems like they're doing the same thing, but they're different implementations.
Swap means if you only need the graph, the swap. I think the diameter is only 2. Yeah, so you can reach anything just by But this torus, the distance is very long. Then you have to cycle it. So there are normally cycles built into the graph. That's why you use increment and decrement.
So is a swap like the simplest?
Yes, yeah, exactly. Yes, yeah. Okay, and then I asked my student, I said, please try this. If you can do this, and then Andrew Charles and others' work will be practically useful, right? Because if that quantum work step can be done efficiently, and then it would be meaningful to me, practically meaningful. But no matter how hard we tried, we couldn't. We simplified it to the one on the left, and then you can do. Yeah, so, well, that's a challenge. Someone please try. Okay, so basically, as you can see, we have lots more graphs to show you, but you can get this flavor. You look at the structure, local structure and the global structure, and the more you can identify, and the better you will be able to do. There is another type of graphs which is sparse. You don't need structure. Yes, okay, this is not our work. Yeah, so we have been really focusing on dense graphs, dense connections. I was talking with someone, hope I see you, and dense matrix has a much wider range of applications because sometimes you do need to connect them more than just sparse to be able to maybe do the cooling. Yeah, if you can connect them in a more complete way, and that possibly can help you to find the ground state more easily. Okay, so this is other people's work. So what do you do if it's sparse? You know where the non-zero values are, and you should be able to do that. So you made this up. If you have a unitary which is sparse, and you construct this. Maybe this is called block coding. So you make the blocks, and then because this H, the H is not, I should use a different symbol. So this H is essentially that, 0 U dagger 0, and that times itself is identity. Because of that, you have this identity. Therefore, you can choose theta to be half pi, and immediately you get that, because that's half pi. This is just IH equals minus I this, and H is that. And therefore, you can take the inverse. You can say this applied to the wave function of useful information at the bottom. That's 0, gets this, and that's this. So essentially, this is what I want to say. So if you want to apply the U, which is sparse, why is sparse? I'll say in a moment. Actually, this doesn't really require it's sparse. It works. And then you just have one oscillator to be 0. And after this, the bottom register will give you the UI. Yeah. That requires this Hamiltonian simulation. And if it's sparse, and then many people have done that. Okay, so let me just do that. Yeah. So I'm moving from the discrete quantum work to continuous quantum work now. And I start with sparse now, because Oda, someone's name possibly there. That's not what we were focusing on. So if you can, I'll just go back. Yeah, so if you can do the Hamiltonian simulation, and you can do the simulation of the U in this way. Okay, sparse. Yes?
So here U is the adjacency matrix of your graph, or what is
Yeah, so here U can be the coin operation, can be the mixer. Yeah.
So why is it useful to implement it as a Hamiltonian simulation? If you have U, can't you compile it directly?
Okay, I'll just do. Maybe I did it too quickly because that was not our work. So what I have shown you earlier is about So some graph has symmetry, and then you can make full use of that symmetry to condense your circuit. Yeah, and then what I was saying is if the unitary has no structure but it's sparse, and then you can use the sparse Hamiltonian simulation to get it done. Yeah, but this is just some math. This works. Yeah. So here, if you construct this circuit, use one oscillator, and if you are able to implement the Hamiltonian simulation, you will get the U. Yeah. Okay. So yeah, I'm sure you expect me to talk about structure now. Yeah. So again, if the Hamiltonian is dense, there is really no efficient way if it's arbitrary. But there are certain types of Hamiltonian, dense Hamiltonian, which can be done. And one of such is if these can be diagonalized by Fourier. So everyone, most of you are mathematicians, so I don't have to explain. So that can be decomposed into its eigenvector formed a matrix, and then that's diagonal, and it's diagonal. So a particular type of Hamiltonian is what is the circulant. Yeah. So why? Because if it's circulant, its eigenvalue and eigenvector are Fourier coefficients and Fourier vectors. So the circulant actually can encode a lot of information, because circulant, the first row is actually quite arbitrary, right? Yeah, so if this is 2 to the power of n, and that has 2 to the power of n piece of information. The second row and the rest of the row are not arbitrary. You just rotate. Yeah. So if you have a Hamiltonian of that structure, and you can use this Fourier diagonalization. So Fourier, quantum Fourier is exponentially fast. This is another inverse Fourier, which is also very, very fast. And then in the middle is diagonal. Okay.
Sorry, for the first slide, what's the complexity with respect to the DFT and the QFT? Is this a circuit depth? So
yeah, so DFT is classical, right? So yeah, so DFT is n log n. Here the n is a capital N. So here the n is the number of, you can see that's n. Yeah, yeah. Sorry, I misused the symbol. I'll change it. Yeah. So basically this is little n by little n, and Fourier is log n squared.
Would you mind saying what is O? I mean, what quantity are you measuring there would be? What is this number measuring?
No, this is not measuring. This is to implement this operator, which is just for
gate complexity. Like they were perhaps asking whether it's gate complexity or Curie complexity.
Okay. So yeah, maybe yeah, because I'm not a mathematician, maybe the vocabulary is slightly different. What I meant is, if you want to do this now is C, okay, and then that can be. So this is n by n in my notation, sorry, and then you would have log n number of qubits. So this is a big block coming out here. That's the wave function, and then this requires log n square steps.
The depth of the circuit.
Yes, circuit depth.
I mean, it's good to at least say what we're talking about, right?
Yeah. Okay, so I said it has this circulant matrix can encode a lot of information, but if every element of this first row is not related, it's arbitrary, and then of course you have to have at least n operations to encode it. Yeah. So under this framework, there is further requirement. That's what I will need to talk about. So first, we need to look at those circulant matrix or circulant Hamiltonian with a smaller number of distinct eigenvalues. Yeah. I only have 5 minutes. Wow. Okay. So complete graph, again, because complete graph has only one non-zero eigenvalue. And therefore, you can see this circuit, this is basically Fourier. And then this is the diagonal. It has only one non-zero values, and therefore, you only need one rotation gate. And this is the inverse Fourier. So that's the whole circuit to implement this operation. Yeah. And what's more, I think I talked with someone this morning at breakfast. It's also time independent. So a lot of people talking about this Tmax is very important because the Tmax is long, and if you do Trotter decomposition, you need many terms. But here, doesn't matter how long. It's just one phase factor. So it's actually the circuit complexity is independent of T. That's also very important. Yeah. So I have to rush through, and I just show you, different kind of graphs. And this one is a Paley graph. Actually, all strongly regular graphs has at most 3 distinct eigenvalues. So all strongly regular graphs we can study.
What is the bracket -8T0 under the R2 gate?
Which one? You mean here?
Yeah.
Oh, yeah. So this is the old the notation. So you just forget about that because that's a global phase. So somehow, long time ago, people define a rotation with angle in the first element, second, but that's redundant. It's not, yeah, I'll remove that next time. Okay, and then, of course, we can study graphs which has all non-zero different eigenvalues, but if they can be computed. So, for example, cyclograph. Actually, cyclograph has the eigen spectrum quite complex. Not complex, but the eigenvalue follows this cos. And also the whole family of Mobius graph. They are all circulant. And the Mobius graph, you can evaluate the eigenvalues, even though they are all different. And then that's the circuit. I think this is by Andrew in his PhD. So what you have is, yeah, so the Fourier, we know is exponentially efficient, inverse Fourier, exponentially efficient. And in the middle, you just calculate. I mean, these functions are arithmetic. And then a bunch of rotations, and then towards the end. So that circuit, so simple. Implement this again. If this one is a Mobius circulant Hamiltonian. And Mobius, we have lots of Mobius-like molecules. They are all very important in protein and DNA, RNA, and so on and so forth. So it's really important. I think I still have many slides, but I'll try to stop. We actually worked, I'm a physicist, right? Yeah, I actually sometimes do experiments. My PhD was an experimental PhD. So we collaborated with people from Bristol and especially Jeremy O'Brien. And Jeremy actually was in my second spectroscopy class. So that shows how old I am. But anyway, so we collaborated with them, and that's the table. I actually played with photons, entangled photons, and beam splitters, and all the polarizers, and so on. So this is so this is the circuit we played, and that implement this graph, which is a complete graph of 4 nodes. And this is not my results, and Jeremy's group's results, but I was part of that. And you can see, so this tiny difference is the difference between theory and experiment. And you can see most of them, they actually just on top of each other. So this is the state tomography predicted by theory. This is the state tomography we obtained experimentally. So I'll rush through, and we can put, if we know how to do graph A and graph B, we put them together. If the 2 graphs are commuting, very simple, okay? And that's how you do. And if they are not commuting, but you can put them in the Cartesian. So Cartesian product you can do. And this is many graphs. Graph can be quite complex, but all I want to really show you is the circuit can be very simple. Okay, and non-unitary, and we did it with quite a few. Yeah, these are all block coding. I just learned that word, but we did it in 2016. And this was done with Sisi Zhou. And so all circulant, and you can use circulant to build more complicated graphs, especially topolers. So you may know more than I do. There was a paper saying almost any graph, any matrix can be built from topolers. And this is how to do the topolers. And then we actually collaborated with a Chinese experimental group in Nanjing and studied directed graphs. And this is to help us to do the page ranking. So hopefully you can see this is a classical page ranking of this graph. So that's 3 is the most important node, 6, 5, 4, 1, 2, 7. And this is our quantum ranking. Yeah, 3, 6, 5, and so on. Yeah, spot on. And so we worked with Jeremy's group again. It's time to implement a Ziggy graph. And that's the graph. And this is the circuit, the quantum circuit. And this is their experimental photonic. And you can see the theory and experiments almost spot on. And we worked with a group in Beijing Computational Science Center, Xue Peng, some of you may know. And we looked at if it's a non-unitary, unitary dilation, and that's Xuepeng's experiments. And again, we did ranking, and this is last year, we did a deterministic search on Xuepeng's apparatus. So summary, so we can do high degrees symmetry and all sparse, and if it can be diagonalized, and if it's non-unitary, we can also do sparse, circulant, topoless, Hankel, and we can put graphs together. Yeah. I want to echo someone made a term quantum numerical analysis. This is actually a textbook I wrote with my PhD student, Josh Isaac, who's now the product manager in Xanadu. And this is essentially numerical analysis of how to solve Schrödinger's equation in the classical sense. So I would like to see a book from someone doing something similar, but with quantum numerical analysis. Thank you.
Thank you for a nice talk.